Problem set for Sunday was 1 through 40. And then this week we've already got 41 to 48 marked up in there. But anything from those, if you're interested, and we can take some time and talk about. Niece? 23. Okay. So there's kind of two possible routes you could go on this. So maybe the part that's throwing you that it's the x is quadratic.
Yeah.
Okay. So you could do this two separate ways. I would probably just start, I would probably start using the y function. And use that to get the t by itself. And then plug that into the x function. And then to get the y by itself, I'd start by dividing by -2. And we'll square root both sides. Doing that's going to get us the plus or minus. And then we'll multiply by 3 and then add 4. So I have something like that. And I think the answer in the back of the book is slightly different because they rationalize the denominator. But like it's close notes, whatever. This is fine. All right. The more difficult piece is the domain and range piece. So what was our interval there? -4 to 3. So the domain, here the x of t is quadratic, so we're going to care about 3 pieces in the x of t, the endpoints as well as the vertex. So the vertex, again, to find that is -b over 2a. So that's just going to be 0 over 2 times -2, still 0. So my x of t there is going to also be 0. Then x of -t. And then my y of 3. So the minimum would be 0, or I'm sorry, is -32, and the maximum is 0. No, maybe we'll just say
So I'm just like you're just plugging in the
endpoints.
into the 2 equations.
Well, just the first equation.
Okay, for the
Yeah, because domain is all about the x, so I'm just using the x equation to do the domain, right? And then to do the range, we're just going to be using the y equation. But since the y equation is linear, all I care about there is the endpoints. Is that okay, Anise? Bless you. Raylan? Which one?
21.
21? Sure. So this one should be not too bad, as it's kind of the same problem, and it's even easier in the with respect to the interval for t, so that's nice. So I'm going to kind of do this the same way. So again, I would do the same thing I did before, where I'm just going to take the y equation and get that equal to t, and then plug that into the x equation and then rearrange from there. So when I simplify that down, y over 2 squared becomes y squared over 4 times a half is negative y squared over 8. So I'm just going to add 1 over, multiply by negative 8, and then square root. So there's that. Is that okay? Okay. So the domain, since the x is quadratic, I care about 3 points. I care about the vertex and then the endpoints. So again, the vertex happens at negative b over 2a. Remember, the b is the coefficient on the linear term, and there is no linear term in that quadratic. So still 0. And then x of 0 is going to be negative 1. Then we just have to check this at negative infinity and at positive infinity. And I'm getting negative infinities for both of those because the quadratic has a negative sign in front of it, so it's pointing down, right? So my domain then is x is going from negative infinity up to negative 1. And the range, because the y coordinate is given by a linear function, all I care about here is the endpoints, but I don't even really need those because this is a linear equation where the domain is all real numbers. So I know like immediately that the range is going to be all real numbers. So you could plug them in and stuff, but here's, you know. Is that okay?
Yeah.
Did I lose you?
No.
You're okay? Others. Yeah, Nat? 17? Sure. So same directions as these previous two. Okay. So I'll take the first equation and get the t by itself. So just subtracting 2 from both sides. Plug that into the second equation. So when I FOIL that out, I get x squared minus 4x plus 4. When I distribute the 2 through, I get 2x squared minus 8x. And then when I add the 3 on, I got plus 11. The domain is coming from the x-coordinate. Now the x-coordinate's a linear function. So since the domain for that linear function is all real numbers, I know the output of that's also going to be all real numbers. So the domain should be pretty easy. Is that okay? And the range then is coming from the quadratic in the y-coordinate. So here I just care about the endpoints in the vertex. Now I know both endpoints are infinity, so like whatever. So again, the vertex is negative b over 2a. So that's 3. And since this quadratic opens up, we're going to go, our range is going to go from 3 to positive infinity. Cool? Okay. It's also a 2. It's the a, the leading coefficient on the quadratic. Others? Anyone else? Maddie? Sure. So again, same directions as all the previous ones. So as we've done on a couple of these others, I'm going to start here with the y-coordinate this time instead of the x, because the y-coordinate's linear, so it's easier to get the t by itself. Oops. So to get the y by itself, I'm going to subtract the 2 over. 2y squared was 4y, so times 3 was 12y squared. And we'll divide both sides by 12 and then square root. And probably the answer in the back of the book, they rationalize the denominator or whatever. I don't really need you to do that if that's fine. The domain here for this. So it's, since the x-coordinate is a quadratic, that's going to, we care about 3 points, the vertex, and then the 2 endpoints. So the vertex is negative b over 2a. That gives me 2. Then I need to do x of negative 8. That's was 64. Oh my goodness gracious. Times 3 is 192, 194, I think. Great googly mooglies. Who picked these terrible high numbers that it's hard to do mental math on? That would be you, Mr. Kulik. Oh. I apologize then. And I plug negative 3 and I get 29. But what do we notice here about my x-coordinate for the vertex? That's not between negative 8 and negative 3, is it? So that doesn't count. So my domain is really just 29 to 194 is just the endpoints. Oh, so sneaky, Mr. Gulek. I mean, they have their moments, the people in the book here. For the range, though, it's a linear function, so all we care about is the endpoints. And that's nice. So I have -4, and then I have -1.5. Does that feel okay? Okie doke. Last call before I move on. Ends. Okay. Anybody else have a preference there? Enzo said anything from 33 to 36. Okay, well, just do 33 then. They're all basically the same. So the way I would do this is I'm going to use my vector equation for a line to do this. Remember, R0 is a point vector, so it doesn't matter which one of those we use. For vector v, we're going to do the head minus tail rule. So that's -4, 7. So my equation for t is, or my equation for x is -1 minus 4t. And my equation for y is 5 plus 7t. And then I just have to figure out the interval for t. Now, the nice part is that it's going to be either, my interval for t is either going to be -1, 0 or 0, 1. As long as you're using the vector equation for a line, that'll always be the case. To figure out which one it is, we're just going to take our vector equation for the line and just do kind of a guess and check here. We'll try plugging -1 in and see what we get. So when I do that, I get -2, which is the other point, correct? So I'm going to do -1, 0. That's it. So again, just as long as you're using the vector equation for the line, finding the interval is just a either or situation. And you just kind of check by plugging in 1 or -1 and seeing if you get the other point involved. And if you do, then that's the interval you take. And if you don't, you take the other interval, since it's a either or situation. Cool. All right. Last chance for the questions. Oh, Allie or Alyssa, sorry. 43. Okay. Oh, yeah. All right. Let's make a space over here. So Jake hits a baseball when it's 4 feet above the ground with an initial velocity of 120 feet per second. The ball leaves the bat at an angle of 30 degrees with the horizontal and heads towards a 30-foot fence that is exactly 350 feet from home plate. Write the parametric equations to model the flight of the ball. Okay. So that's going to be the initial velocity times cosine of theta t. And then for y, that's -16t squared plus the initial velocity sine theta t plus the initial height. So that's part A. Cool. Part B says if no fence or any other obstacles were present, find the distance it would take or the ball would travel when it first hits the ground. So hitting the ground is a height, right? Specifically, the height would be at 0 when the ball hits the ground. So I'm going to be solving y of t equal to 0. So to do that, I'm going to use the quadratic formula. So alpha y equals fraction mode. So I have negative b, so negative 120 times sine 30. Then I'm going to have plus or minus. I can't do a plus or minus on my calculator, so I just have to do them one at a time. So I'll do the plus sign first. Square root of 120 times sine 30 squared minus 4 times a times c divided by 2 times a. So negative 0.07 or if it was a subtraction problem, I'll just press alpha y equal or alpha and enter to recall the last thing I had written and then just go back and edit the plus to a minus. 3.82. Now clearly the one we want is the positive one, right? Time really isn't negative. And then C says, will the ball clear the fence? Well, to do that, we need to know the time it takes to get to the fence. So that's the time it takes to go 350 feet. So basically, we want to do y of t350 and compare that to 30 feet. To get t350, we're just going to take and plug that into x. So 350 divided by 120 times cosine 30. So that's 3.37-ish seconds. So y of 3.37 and I think when we did this in class, I was using my using the calculator to do these calculations that I'm now kind of doing by hand-ish. You could still use your calculator to do this. I didn't start by looking at a picture though, so I get that we're 24.59 feet, which is less than 300 or 30 feet. So no home run, but that ball's still not catchable. Since it's defined catchable as 10 feet or less off the ground. So that's too high for the outfielder to jump up and catch before it hits the wall, but not so high it's going to get over the wall for a home run. It's probably a double. Baseball players out there, if you bang one off the wall, you're usually getting 2 bases out of that. Or more if you're speedy, or the outfielder's bad. Or maybe less if it's a short field. Who knows? I don't know. 350 feet is pretty far, though. If you bang one off that fence, I'd be surprised if you get less than 2 bases. But it could be real slow, and the outfielder could have a really good arm. I feel like back in the day, Cecil Fielder turned a couple of those into singles. He used to play for the Tigers. He was a big, giant, slow person. He was like the first guy to hit 50 home runs in a season in like 30 years, though. It was a pretty big deal. Back in the early 90s or something. Anyways, Alyssa, happy? Yeah, no problem. You got a bunch of extra baseball trivia from Mr. Kulik's childhood to go along with that, so. Okay. We ready to get going then? We've done a bunch of exam or questions here. We can always come back and get some more next time too if we need to. All right. Today, we're talking about the polar coordinate system. So previously to this point, we've been using the Cartesian coordinate system to graph things. That means you have an x and y coordinate. Now, in the previous chapter, we defined parametric functions different than Cartesian functions, but we still plotted the result of our parametric function into a Cartesian space. All right, we're still plotting x and y's. You guys remember that? Today, we're going to be talking about a wholly new system called the polar coordinate system. So let's just start with a definition here. So we have that a point in the polar coordinate system, I'm just going to refer to that as PCS, because we're probably going to write that 20 times during the lesson, and it's a lot of letters that I can save by just saying PCS. Plus, it sounds really technical, like we know what we're talking about. Is defined by the general form r comma theta, where r is the point's distance from the origin, and theta is the measure of the angle that gives the terminal side for the point's direction. So let me just grab this and copy us in here. All right. So what we have here is a picture of polar graph paper. It's not a spider web. So the concentric circles, we know what the word concentric means?
Scale. Each other, right?
They have the same center, right? So they're all like one is inside of the other. Concentric, meaning sharing the same center, are representing the r's. So the first circle is like r equals 1, and then 2, and then 3, and then 4, and then 5, and 6, and 7, and 8. You get the idea, right? I'm going to erase this and get it out of here because it's going to get pretty busy pretty quick. So this first line and the vertical or the diagonal lines here representing our angles. So this is like pi over 3. Come on. There we go. Where does it? What is it doing here? This makes sense, right? Half of one screen on, half of the other.
Mr. Bullock, but that does not make sense.
No, I agree. My output were all jacked around. Are we gonna? We got it, computer. What? Okay, there we go. All right, good. So here are my diagonals. Well, this is what it's so angry about. So that one's like pi over 3. This would be like, well, I guess this is 0. 2 pi over 3. What am I? No, Mr. Kulik. Don't write down what Mr. Kulik's doing. He's stupid. Oh, okay, there it is. So it's pi over 6. That makes a heck of a lot more sense. This is pi over 3. There we go. That's pi over 2. And this would be 2 pi over 3, 5 pi over 6, pi, 7 pi over 6, 4 pi over 3, 3 pi over 2, thank you, 5 pi over 3, and then 11 pi over 6. Everybody okay with that idea? Okay. So to some extent, we're going to have to be doing some estimations. And remember that all of these could also represent degree measures, right? So like 30, 60, 90, etc. Everybody's okay with that? You could count around by 30s and just do the same thing in degrees if we wanted to. Okay. So let's just do a couple of examples. So let's do 3, 120. Actually, let's do them in colors. So 120 is the same as 2 pi over 3. So I'm going to be on that line somewhere. Everybody agree with that? So 1, 2, 3. Is that okay? What if I have negative 2 pi over 3? Uh-oh. What do we do with the negative? Well, pi over 3 is going to be this line, right? Everybody agree? But because it's negative, we're actually going to put it on that side. So then we're going to go 1, 2. Okay there? Okay. Negative 100. Same thing as positive 260, right? Everybody's cool with that? Which is like right in here-ish. Everybody's okay? I draw my own line in there. Yes? But because it's a negative 1, I'm going to have to flip it across. So like we're there. Do you guys feel okay about this? About plotting these guys? Not that big of a deal, but like takes a little bit of practice. Now I want to point out to you something here. If we're looking at that second example, negative 2 and pi over 3. Can we observe that this is also the same thing as positive 2 and 4 pi over 3? Everybody see that? And wouldn't that also be the same thing as like negative 2 and then 7 pi over 3? Right, where we go around one full rotation and then flip. Still puts us at the same spot. So guess what we're going to have here? How many ways can we represent a point? A lot, and that a lot word is really infinitely many. Good. So let's kind of define that formally here. Oh, Boise. So given some point r comma theta in the polar coordinate system, any other point that coincides, what do we mean by coincides again? So that means it's in the same place, right? Coincides means they're like right on top of each other. Coincides with P, must be of the form
GUI after PCS.
any other point.
Oh.
Okay, so it means we have to be coterminal to the angle in P, or it has to be flipped. And we could say the same thing in degrees as well, right? So this is just stating the same thing, but in degrees. Oh. If I wrote in degrees. Okay, so let's say we want to find all the polar coordinate points that coincide with 8 comma 5 pi over 6. So the first set of points would be the ones that are coterminal to theta, right? The same thing plus a 2 pi n. And the other set would be the ones that are negative and coterminal to that. Now typically we want to reduce that second one. So 5 pi over 6 plus pi is 11 pi over 6. But that's it. We're just using those formulas. So no big deal. What if we have root 2 and negative 234? Well, we're going to have root 2 and then everything coterminal to 234. Recognize that because this is in degrees, I'm adding 360 instead of, or multiples of 360 instead of multiples of 2 pi. And then we also need negative root 2 over 2, and then negative 234 plus 180, and then coterminal to that. So again, when we simplify this down, that's negative 54 plus 360. Again, where n is some integer. Does that feel cool? Okay. Next thing we'll want to do is just talk about converting back and forth between a polar point to a Cartesian point. So the two things that the things we're going to need are all things that you know. So the first two we're going to use going from polar coordinate point to a Cartesian point, and the second two we'll use to go from Cartesian point to polar coordinate point. And these are all things we recognize, right? That the first two were the just the one of the old definitions of sine and cosine. Remember, cosine was x over r and sine was y over r, just rearranged. And the second two are just our definition of the Pythagorean theorem and then the tangent definition from the unit circle. So like, no big deal. Okay, so let's say we want to take negative 3 over 2 and convert that to a polar coordinate point. Well, to get my value for r, I'm going to start with the Pythagorean theorem. So I get the square root of 13. Then if I think about the plot of negative 3, 2 is here. So if I draw the terminal side of that, there's my theta. So there's my alpha. So I know theta is going to be 180 minus alpha, where alpha is the tan inverse of the absolute value of y over x. Maybe I'll write in the numbers here. 2 over negative 3. Make sure my calculator is in degree mode. Oh, good. Because I think I'll give this as degrees, don't you? If my radians aren't going to be like a unit circle value. And notice when I'm typing this into my calculator, I'm not bothering at the absolute value because I did the absolute value part in my head. That's why it's tan of 2/3 instead of tan negative 2/3. So I get 146 and some change. So I have square root 13, 146.31 degrees. What do you think? And how many times have we done like this little problem is something, right? Boy, it feels like that's cropped up in almost every chapter. What if we want to take negative 3, 148 degrees to Cartesian? Well, here there's like almost nothing to do. Just like typing it into the formula and I'm done. What, Mr. Kulik? Yeah, dude, it's that easy, man. So I have 2.54 and then negative 1.59. Any questions about anything we've done here? I think we'll stop here. This feels like a good stopping point. I don't want to get into polar functions here yet today. So let's see, what can we do now? You guys can do up to 62. 49 to 62. We're worth pointing out. What else did I tell you guys was going to be happening this week? Homework quiz. What haven't we done yet? What can you be pretty sure is going to be happening next class?
Not a homework quiz.
I question sometimes your logic abilities here. Also worth pointing out to you guys that I didn't include it in the OneNote is polar graph paper, that if you want to use that to do like the homework problems or they're asking you to like graph like polar coordinate points, like we asked you here, like that could be helpful to you if you wanted to use that. Just for practice and stuff, you know.
Would today's lesson be on homework?
No, homework would really be up through what we did last week.